Welcome to the deep dive. We're jumping right in today with some really interesting sources that are challenging how we think about aligning large language models after pre-training.
That's right. We're focusing on mode collapse, when these really capable models start sounding, well, kind of repetitive. They lose their diversity and just keep giving the same sort of stereotypical answers.
Yeah, it's super frustrating. And usually we blame the algorithms, right? Like maybe the reward model wasn't good enough or RLHF itself has limits.
Exactly. But this paper we're diving into flips that script. It argues the main culprit isn't the algorithm, it's actually in the data we use to train it. They've identified something they call typicality bias.
Typicality bias.
Right.
So a bias in the human preference data itself, that's quite a different take.
It really is. It suggests it's a systematic, almost psychological thing baked into the annotations. And the best part, they propose a fix that doesn't need retraining. It's a prompting strategy called verbalized sampling, or VS.
Okay, intriguing. A data-level problem with a training-free solution. So our goal today is to really unpack this typicality bias, where it comes from, how they formalize it, and then get into the nuts and bolts of verbalized sampling and the evidence showing it actually works.
Let's do it. So where does this idea of typicality bias even come from? Well, the researchers trace it back to cognitive psychology. Things like the mere exposure effect. We tend to like things just because we've seen them before.
And processing fluency stuff that's easy for our brains to chew on feels better somehow.
Precisely. And the availability heuristic, we overestimate the importance of information that easily comes to mind. So the hypothesis is that human annotators, when comparing model outputs, subconsciously favor text that feels familiar, fluent, predictable, basically typical.
Even if it's not actually better in terms of, quality or helpfulness for the task.
That's the key claim, independent of true quality. They argue we've accidentally trained models to mimic this human cognitive shortcut.
Okay, so how do they nail that down mathematically? They have a model for the reward function, right?
Yes, equation 1 in the paper. They model the observed reward, true xy, as the sum of the true task utility, plus this bias term.
And the bias term captures this typicality thing.
Exactly. It's written as alpha log pi ref yx day. Now, pi ref y is the probability the base model, the one before alignment, assigns to the response given the prompt $6. It's basically a measure of how natural or typical that response is according to the pre-trained model.
So delta chi ref is the proxy for typicality. And the crucial part is the coefficient, alpha.
Right. The coefficient alpha, they argue and then show empirically that alpha is greater than 0. A positive alpha means higher typicality directly increases the reward score, even if tell true is held constant.
So more typical equals higher reward, all else being equal. Did they test this?
Oh, yeah. They use data sets like help steer. They found pairs of responses, thousands of them, about 6,874 pairs, where the actual correctness level was identical. So delta correctness was 0.
Okay, so no difference in actual quality.
None. And yet, they could still estimate this typicality weight. For Llama 3.1, it was around 0.57, and for GLM 4.5, about 0.65.
Wow. So what does that mean in practice? Like, how much more likely is the typical answer to be preferred?
It translates to the more typical response having something like 1.42 to 1.47 times higher odds of being picked as more helpful by the human annotators. It's a solid confirmation of the bias, independent of actual quality.
Okay, that's the bias explained. But how does that mathematical bias actually cause the model's outputs to collapse into just a few modes?
Good question. It comes down to how RLHF optimizes the policy. The math shows that the optimal policy the model learns, let's call it tilde, gets skewed. It becomes proportional to the base model's distribution raised to a power.
Equation 3.
Propto gamma.
Exactly. And this exponent, gamma, is calculated as $1 plus alpha beta, since we just established that alpha is positive and beta is generally positive in these setups.
Then gamma has to be greater than 1. Right. And raising a probability distribution to a power greater than 1, that mathematically sharpens the peaks. It squashes the probability down towards the things that were already most probable, the modes of pi river.
So especially when there are lots of equally good answers, like in creative writing.
Exactly. When Fruse is flat or there are ties, typicality, thanks to that positive alpha, becomes the deciding factor. It acts like a tiebreaker, pushing the model to output only the most typical stuff and killing off the interesting, diverse, less common responses. That's mode collapse, driven by the data bias.
Okay, so the problem is baked into the data itself via this typicality bias. How do we fix that without throwing out all our preference data and starting over? Which seems impractical.
Yeah, exactly. Retraining is expensive and maybe wouldn't even solve it if the bias is fundamentally human. This is where verbalized sampling, VS, comes in as a really clever training-free approach.
Training free is always nice to hear. What's the insight behind it?
The core idea is that how you ask the model for an answer actually changes which mode it tends to fall into. They observed different prompting strategies lead to different kinds of collapse.
Okay, like what?
Well, if you just ask for one thing, like tell me a joke, that's an instance-level prompt, the model tends to give you the single most typical joke it knows, the absolute mode.
Right, the one it thinks is most probable based on pi plus the bias.
Then if you ask for a list, say tell me jokes, a list-level prompt, it behaves a bit differently. It tends towards giving you distinct items, but distributed more uniformly among related typical items. Still kind of collapsed, but maybe not to just one single output repeated.
Okay, so how does VS get around both of those?
VS uses what they call a distribution-level prompt. Instead of just asking for jokes, you ask the model to essentially think about and verbalize its own internal distribution of possible jokes.
Verbalize its distribution. How does that work in a prompt?
It's surprisingly direct. You'd prompt something like, generate jokes, and for each joke, state its probability. You're explicitly asking for the outputs and their corresponding likelihoods.
Ah, I see. So you're forcing it to perform a kind of meta-reasoning about its own output space,
Yeah.
rather than just picking the single most likely thing according to the biased reward.
Exactly. By asking it to generate the distribution itself, the mode of the model's output becomes an approximation of the entire pre-training distribution before it got sharpened by the typicality bias during alignment. It unlocks the diversity that was suppressed.
Let's make that concrete with the paper's example, the coffee joke one.
Right. Direct prompting for 5 coffee jokes might give you, why did the coffee file a police report? Because it got mugged 5 times in a row. Classic mode collapse.
Painfully familiar. And with VS.
With VS, you'd get 5 different coffee jokes, and crucially, each one comes with a probability attached, like joke 1, probability 0.12, joke 2, probability 0.07, joke 3, probability 0.15, and so on. The model is showing its work, showing the spread.
That's actually quite elegant. It's just a prompting trick. No retraining needed.
And it's model agnostic. They also tested a couple of variations to boost performance. There's VSQT, which adds a chain of thought step to help the model reason better about assigning those probabilities.
Okay.
And VS Multi, which uses multiple turns, kind of iteratively refining this sample distribution.
All right, so the theory sounds good. The mechanism seems plausible. But does it actually work in practice? Let's look at the results. First up, creative writing.
Yeah, poems, stories, jokes, the kind of tasks where diversity is really what you want. And the results were pretty clear. Standard VS, just the basic version, increased semantic diversity by about 1.6 to 2.1 times compared to just directly prompting the model.
That's a solid jump. But often, when you increase diversity, quality takes a hit. Did they see that trade-off?
That's the interesting part. The enhanced versions, VSQT and VS Multi, actually managed to hit the highest diversity scores while also maintaining top-tier quality scores, according to human judges.
So pushing the Pareto frontier, getting more diversity without sacrificing quality.
Exactly. It shows you can break that typical trade-off. And another really key finding was how this scales.
Scales with model size.
Yeah. The bigger, more capable models, they mentioned things like GPT 4.1, Gemini 2.5 Pro, they benefited way more from VS. Their diversity gains were like 1.5 to 2 times larger than what smaller models got.
Huh. So VS might be particularly good at unlocking the latent potential hidden by alignment in these really large models.
That seems to be the suggestion, yeah. Now, moving away from creativity, what about tasks where you want the model to reflect a real-world distribution? Like open-ended QA.
You mean like name a U.S. state where there's no single best answer, but there's an underlying distribution of how common state names are?
Precisely. The goal here isn't just diversity for its own sake, but aligning the model's output distribution with some reference distribution, like how often states appear in the training data. They used KL divergence to measure this.
Okay, and how did VS do?
Direct prompting was pretty bad. They saw one model, GPT 4.1, output California something like 95% of the time, which, is not representative. The KL divergence was huge, like 14.89.
Yikes. Complete collapse.
But with VS standard, the KL divergence dropped dramatically down to around 0.12 or 0.13, much, much closer to the reference distribution they estimated from the red pajama corpus.
That's a massive improvement in reflecting the actual underlying data distribution.
Yeah.
Did it help with coverage too, like generating more unique states?
Absolutely. VS significantly boosted what they call coverage N, which is basically the fraction of unique, known ground truth answers, in this case US states, that the model managed to generate.
Okay, creative tasks, distribution alignment.
Yeah.
What about synthetic data generation? That's a big use case.
Right. They tested generating competition math problems, which need a lot of diversity in style and difficulty. They used VS with models like GPT 4.1 and Gemini 2.5 Flash to create datasets.
And then use that synthetic data to train other models.
Exactly. They fine-tuned smaller models, like Huen variants, on the data generated by direct prompting versus the data generated by VS. And the results downstream were pretty consistent.
Don't tell me. The VS data was better.
Yep. Models trained on the VS-generated math problems performed better on actual math benchmarks, like Math 500 and Olympiad Bench. The VS multi-version produced data that led to the highest average accuracy, around 37.5%.
So the diversity unlocked by VS during data generation translated directly into better performance for models trained on that data. That's quite compelling.
It really underscores the value of getting those less typical, more diverse examples, especially when you're bootstrapping and fine-tuning.
Okay, so VS boosts diversity, helps align distributions, and even improves synthetic data. But whenever you mess with model outputs like this, especially pushing towards less typical stuff, you have to ask, does it break anything important, like factual accuracy?
That's a critical question. They checked this using common sense reasoning benchmarks. The good news is, no, it doesn't seem to break accuracy. The VS method scored comparably to strong baselines like chain of thought prompting on metrics like top at 1 and pass at N accuracy.
So the quality holds up in terms of correctness. What about safety? Pushing a model away from its typical aligned responses sounds potentially risky. Could this be used as a jailbreak?
That was definitely a concern they investigated. They used the strong reject benchmark to evaluate safety alignment, and again, the results were reassuring.
How so?
VS maintained really high refusal rates for harmful requests, consistently over 97%. The drop compared to direct prompting was tiny, like less than 1 percentage point, maybe 0.3 to 0.8 points.
There's not a significant jailbreak factor, then.
Doesn't appear to be. Interestingly, even when VS did refuse, it often generated more diverse refusal statements rather than just spitting out the same canned rejection over and over, which in a way further confirms the alignment is holding, just with more variety.
That's actually kind of neat. Okay, so accuracy and safety seem largely preserved. What about controlling the amount of diversity? Is it tunable?
Yes, and this is another cool aspect of VS. Unlike tweaking decoding parameters like temperature, which can be a bit fiddly, VS lets you control diversity directly in the prompt itself. You can literally just add a condition to the prompt like, generate responses with probabilities below some threshold T. By changing that threshold T in the text of your prompt, you can systematically dial the diversity up or down.
Ah, that's very direct. A prompt-level control knob for diversity.
Yeah.
Baselines don't really offer that.
Not in the same explicit way, no. And finally, they looked at whether VS replaces or complements existing decoding strategies. You know, things like temperature sampling, top-at, MIMPI.
Right, do you use VS instead of those or with them?
The ablation study showed it's complementary. You can use VS together with standard sampling methods. Combining VS with, say, temperature sampling consistently resulted in better diversity quality trade-offs than using either method alone.
Okay, so it adds another tool to the toolbox, works alongside of what we already use.
Precisely. They demonstrated this across various models too, like Qwen 3235B and Llama 3.170B. It consistently pushes that Pareto front forward. Hashtag tag outro.
All right, let's wrap this deep dive up. It feels like we've landed on two really significant takeaways here.
I'd agree. First, this compelling argument and evidence that typicality bias in human preference data is a major, maybe even primary, driver of mode collapse. It shifts the focus from purely algorithmic limits to the data itself.
Right, a fundamental data-level insight. And second, the practical solution, verbalized sampling, a simple, training-free prompting technique that seems remarkably effective at restoring the model's inherent diversity by making it reason about its own output distribution.
It's principled, it's practical, and the empirical results across creative tasks, distribution alignment, and synthetic data seem really strong.
So for you listening, especially if you work with these large models, the upshot is pretty clear. You might not be stuck with those frustratingly repetitive outputs. VS offers a way to potentially unlock much richer, more diverse responses.
Particularly from the most capable models, without necessarily compromising core alignment like safety or factual accuracy. It's about getting more out of the models we already have just by asking them questions in a slightly different, more distribution-aware way.
Okay, let's leave our listeners with a final thought, something maybe looking a bit further ahead based on the paper's outlook.
Well, they touch upon the potential of using VS not just for generating final outputs, but within other ML systems. Specifically, they mention its promise for improving exploration and reinforcement learning.
Ah, so using VS to generate a wider, less typical set of possible actions or hypotheses during the RL training process itself, like in RL systems, maybe using techniques like RL2.
Exactly. If VS can coax the model into suggesting more diverse, less obvious next steps or rollouts, that could potentially make the exploration phase of RL much more efficient and effective. It could lead to discovering better overall policies.
So the real long-term impact of VS might not just be getting more interesting poems or jokes today, but actually helping us train smarter, more robust, and perhaps more globally optimal AI systems tomorrow by improving how they explore possibilities.
It's a really interesting prospect. Using this technique to unlock diversity, not just for us, but for the learning process itself, definitely something to mull over.